Welcome everyone to the 2024 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from Mahesh Krishnamurthy, a co-founder of Vayu Robotics with more than 15 years of industry experience. Mahesh earned his doctorate in silicon photonics and is joining us to teach viewers about Plenoptic cameras for AI and advanced mobile robotics. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me, Mahesh. We appreciate you for taking the time to present at the 4th Annual Vision Spectra Conference.
So thanks a lot for joining. My name is Mahesh. I'm one of the co-founders at Vayu Robotics, and today we'll talk about Plenoptic cameras, and I'll go through some advantages we can have by using them. So to start with, I just want to give you a brief intro about who we are. So we are a delivery robotics company, and as you can see here, we are building a full delivery robot solution, which is based on two foundational pillars of technology that we have built. One of them is using the Plenoptic camera, which you can see on the robot. It has 6 of those for surround vision, and it helps bridge the gap between a very expensive LiDAR system and a very inexpensive stereo camera system, which is currently being used. So as you can see, this can go autonomously on public roads on a bike lane. So it's intended to work like a bicyclist. And our main belief here is that autonomy, for it to be adopted in the real world, we would have to start with something which is super safe. So we have dialed down the speed and the weight of the system, so it operates like a bicyclist and also makes unit economics work with this form factor. So what am I going to talk about today is this sensor that you can see. What I'm going to talk about today is this sensor that you can see here. So we've built this sensor over the last 2 years that we have been at this startup, and it's a Plenoptic sensor. As you can see, it has 4 apertures in front to capture various aspects of the light field, and it has 1 output at the back for both power and data. And all the compute is happening either at the edge or on a central compute that can be connected to this camera. So before I go into the details of how this actually works, I just want to give you some very basic overview of what this image sensor is about. So there are aspects of the light field which have been used until now, which are basically wavelength and intensity. So a black and white camera just counts the number of photons that is going to come at the image sensor, and a color sensor captures the wavelength information of light. But the Plenoptic function has a lot of other dimensions which we are exploring in this technology, and I'll show you results to explain what are the benefits of doing that. And before we go into that, I'm a big believer of the fact that highly focused small teams can do a lot of very productive work. So I want to thank the people who made it happen. So they're all like super, closely knit team members that we work with on a day-to-day basis. Raj, who's an electrical engineering lead, George, who's a computational imaging algorithms lead, Jason Ashton, who was our software integration lead, and Jeff, who works on the mechanical engineering aspects of the sensor. And I would also like to thank Econ Systems, who were our manufacturing partner in bringing this technology from an idea to a real sample. So thanks a lot to all of these people, and this would not have been possible without very strong contribution, burning midnight oil for a lot of days. So let's get into what problems we are trying to solve. So as you can see, the industry is kind of split between having very, very highly optimized systems where redundancy and safety are high priorities. Like, for example, on the left, you can see the Waymo vehicle, which has more than 50 plus sensors. It works super reliably, and it has multiple layers of redundancy in terms of LiDARs, radars, cameras, ultrasonics, and thermal cameras, and a lot of other sensors. And they have cross-functional redundancy, which makes it super safe. On the other end of the spectrum, you have the Tesla Model 3 approach, which is primarily operating on RGB cameras with vision input only, but it is super optimized for scaling this technology to millions of units, but it has very poor coverage in corner cases. And what this means is it can work very well in a nominal scenario, but when you have some corner cases, which is what is blocking autonomy today, it has a big challenge open to be solved. So what at Vayu, what we are trying to do is we are trying to come up with a sensing solution which is jointly optimized for both safety and scalability. And the key question the industry has been facing all this while is, does a sensor like that exist? So how do we solve that problem? So let's go into some of the issues of the Tesla type approach, which is purely vision. So what happens is, just to give you some background, the way the stereo vision systems work are they look for correspondence between the left image and the right image. And as you know, most of the world that we encounter is fairly low in texture. What I mean by that is most of the cars, roads, building walls, they have very poor texture, which means that the correspondence between the left image and the right image is very hard to match. And when that happens, it creates a lot of these gaps, which lead to very poor fill factor in the outcoming depth output. So what happens is it leads to a lot of false negatives, and that's not very ideal if you want to build a safe system. And how do we solve it? So you can either solve it by using very expensive sensors where you shine very high energy photons into the world, like lidars, and you get a real-time measurement at every point in the world. Or you can exploit other aspects of the light field which is completely passive. So you rely on the illumination from the sun or artificial sources providing the photon for illumination, and then you capture the image, just like how humans and biological systems operate or move around in the world using those sensors. So how does that actually work? So what are these dimensions that we are trying to probe? So as I briefly touched upon in the very beginning, a photon is an oscillating electromagnetic field, right? So what you see here is the blue plane is the electric field plane where the electric field oscillates, and the red plane is where the magnetic field oscillates. So if you look at the life journey of the photon from the sun all the way to the image sensor, it can be modeled pretty accurately. Like the physics and light matter interaction is very deeply understood, that you can actually predict where the life journey of the photon all the way from the sun to the image sensor if you capture certain aspects of the light field. So it can tell you a lot about what happened to the photon when it comes from the sun, what it hit on its path, and how long it took, and all of those things. So what we do is we have some customized optics to probe the plane of oscillation of the electric field in front of the image sensor, and we use standard CMOS image sensors from high volume customers like high volume vendors like Sony and other people, and we use our software algorithms to derive meaning out of this. So what I mean by that is 2-3 years back, transformers were not a very big thing in imaging systems. So now with the advent of transformers, what we can do is we can extract a lot of information out of these types of images that come into the neural networks. So by having a combination of exploiting the light field and also the transformer technology, we are able to produce a very dense depth map along with an enhanced RGB image, and also get shape of objects and material properties at a coarse level that helps in navigation. So this is what we are trying to do. And in future, we also have other aspects such as wavelength, which we plan to exploit to make the advantage of using Plenoptic sensing way more than what we can today. So I'm going to show you some results of what can be possible with this. So as I mentioned, I'm going to show you some results of our sensor mounted on a vehicle and driving around in the parking lot. So there are a few outputs that you get out of the sensor. So you get a baseline image, and then you get a very dense depth map. And if you observe, the depth map has a lot of rich features like the lines, electric cables on the top, and you also get shape of the world. So green here is pointing upwards, and anything non-green like purple or magenta is pointing in some other directions. So this helps a lot in coming up with the occupancy map, which can be used for navigation, and it provides a shortcut to it instead of going through the perception blocks and the semantic segmentation blocks. In addition to that, what we have are two other proprietary channels, which are proxy for texture and material property. So this is super important because if you just use the baseline RGB image or grayscale image, you can see that in the top part of the image, there is very poor texture because of low light. But since we probe other aspects of the light field, we are able to get a lot more information out of these images. Like the texture image shows you a lot more features, and then the material property also tells you what is bright and what is not bright. And one cool thing about this is the signal that we probe is inversely proportional to the albedo or the reflectivity of the materials. So what happens is anything that has very dark features show up as very high signal through the sensing approach. So what happens is some things like a black tire and like black objects, dark objects, they show up very strongly. So that's something that I wanted to point out, because this is how we bridge the gap between using a very basic stereo camera type approach versus using this Plenoptic approach to come up with highly texture rich information that can be used to refine our depth map. And it has various applications. To name a few, like it is very useful for AMRs, ADAS, driver assist systems, delivery robots and autonomous vehicles and humanoids. So it has any robot that needs to see the world. This could be useful, stationary or moving. So both these areas are quite relevant for this technology to be adopted, and there's a lot of value to be added to existing methods that are being used in these industries. So I'm going to show you some examples. So this is an example of how it performs on a highway, primarily focused on ADAS applications. And as you can see, the vehicle is going on a highway 101 at around 65 miles per hour, and you can see that the depth is quite crisp. So the next app, so this can be used for ADAS applications and even autonomous vehicles on a highway. The next application is for delivery robots, which start to operate on the sidewalk. And you can see here that for a slow moving robot, we have a very wide field of view, around 125 degrees. And the Plenoptic function works very well across the whole range, and you can see the depth map here showing up, which corresponds to the RGB image on the left side. So these are also applicable for sidewalk robotic applications, like meaning there are a lot of companies who are currently doing delivery on the sidewalk. So this could be used by those industries. In addition to this, not just in outdoor where you are fortunate to have the sun's illumination, even in indoor environments where you have artificial illumination, this technology works pretty well and transfers very well to indoor environments. So here is an example of our robot going around in an indoor environment within our office at Playground Global in Palo Alto, and you can see the quality of the depth point cloud come out pretty crisply. There are areas where it does very well, and then there are areas where it still needs improvement, and that's where we are trying to add some more dimensions of the light field to make it close the gaps where we currently have issues remaining to be solved. So these are three examples of it operating in real time to tell you how good the performance can be. Like, for example, things like glass, very shiny surfaces, which are usually hard to detect using LiDARs. This technology, Plenoptic technology, could be very useful to detect things which are very challenging for traditional sensing methods. So I just wanted to share how it compares with state of the art. So let me first start with existing products that serve this market. So here is an RGB image and a comparison image with an Intel RealSense showing a depth map which is fairly coarse, and on the right side you see the depth map from this technology. And as I mentioned before, there are a lot of the fill factor is not very high for the Intel RealSense due to reasons of not being able to be matched because of the RGB image not having texture, but using our sensor, we are able to produce a much higher quality depth map. So it performs really well and is also at the similar cost point, right? Because these are all standard CMOS image sensors with customized optics, which are nothing special about them in terms of there are no exotic materials used. So the BOM cost is very comparable to what an Intel RealSense costs today. So moving on to, so this is a comparison with a very, very high volume state-of-the-art sensor, which is used in most robotic applications. And we can show that we are doing way better than that. So it would be a right option to use if you are open to changing the sensor configuration on your robots. Moving on to outdoor applications, I'm going to show you some comparisons between our sensor and a LiDAR. So here we place some very hard objects, which is like a glass container, a very small concrete block, and a black bin. So these are typically used to stress test sensors, and this is also placed in the direct view of the sun. So we're going to show you how our sensor compares with a 128 channel LiDAR, which has around point 1 or 0.2 degree angular resolution on the horizontal and vertical, depending on the settings. And here you can see the first thing you would notice is that the image on the depth map on the left has very high angular resolution. It almost around 10x, and it can also see the wires on the on the sky on the electric post. So what happens here is for a very low cost, you're immediately getting around a 10x increase in the angular resolution, because you're using an image sensor which has very high instantaneous field of view compared to a LiDAR system. And all of this is possible with no moving parts, and it's a real solid state device. And the other thing I wanted to point out is there are some objects which are very hard to see by a LiDAR. So these are the objects which we placed on the ground, which are very hard to see. But on this area, you can see that all the 4 objects that we placed on the ground are easy to be picked up. And that shows the power of this technology in addressing some of the corner cases that is holding autonomous deployment in the real world today. So this is comparison with a very expensive long-range LiDAR, which is currently state-of-the-art in the industry today. Now, comparing it with Mobileye, which is quite widely used as well, I'm going to show you some real examples of how a Mobileye system works and how our system works. So one of the things that Mobileye struggles with is sun glare. And here there is a clear example of us able to detect which photon is reflected and which photon is scattered, and we are able to remove those photons, resulting in a very high quality image which has no glare in it. And if you use this in all upstream tasks like semantic segmentation, trajectory planning, object detection, tracking, and things like that, your upward tasks have a lot more fidelity compared to using an image which has a lot of glare in it. So that's kind of the comparison with Mobileye today. And in terms of the technical specifications, since we are a startup, we optimized for speed of execution. So there is definitely room for improvement in the form factor and various other metrics that we have. But I just wanted to point out that currently we are using a 2.1 meg full HD resolution, 1920 by 1080, and the power consumption is only 5 watts. And we have 2 configurations, 120 degrees and 40 degrees. 120 is primarily used for near range applications, and then the 40 degree is used for longer range applications. And it has all these specifications listed here, and you can modify it, and they are all a function of the image sensor that you use. So if you wanted to change the image sensor to something else that is more preferable for a certain application, you could always do that. So this technology is not married to what image sensor is being used. Like you could use an 8 megapixel image sensor or a 17 megapixel image sensor, and it would still transfer, all the benefits would transfer. So now I'm going to talk a little bit about how this technology can be used to minimize accidents today that no other sensing technology is able to solve. So one of the things that I wanted to talk about is slippery roads are responsible for a lot of accidents, and black ice is a very, very commonly encountered phenomena during the winter time in a lot of places across the world. So here is an example that I showed of what happens when when the road looks fairly similar, but actually has ice on it and you're not able to see it. So what we do is, here is a controlled experiment. So here is an experiment showing that there are 3 trays of asphalt, and each of them have a different material on top of them. So one is water, the other one is dry, and the other one has oil in it. So oil and water cause the slipperiness in the surface, but in the RGB image or the monochrome image, you can see that the image looks exactly the same. So to a human observer, you would not be able to tell the difference between whether there is oil on the surface or whether there is water on the surface or it's dry. But through the Plenoptics technology that we are using, we get some signals which are proprietary to us, which tell you the contrast between a dry surface and a slippery surface like oil or water or ice. And we have also tested this not just in a controlled environment, but also in a real world, where you can see that this is a very normal day in Tahoe, and you can see that this area has a lot of ice, but you cannot tell the difference between whether it's dry or whether it has ice on it. Whereas when you probe these other aspects of the light field, you're able to get very good signal from areas which are dry and not dry. So that gives you a very strong indicator of whether a surface is dry or slippery, and that can be used for tasks which you could use, tasks like semantic segmentation, which you could do uh, for your sensor performance optimization, where you can have it on an ADAS system, and that can give you warnings on whether a road is going to be slippery, or you need to slow down or things like that. So this has a very big very big opportunity to make it into ADAS vehicles, where you can improve the safety of these vehicles during winter time. The next thing that I wanted to point out was the effect of sun glare. So sun glare, this was surprising to me when I was researching about it. It apparently is responsible for 9% of accidents that happen in daylight. And I've encountered it, and you've probably encountered it as well. So what we try to do is, just as we all wear polarized sunglasses to minimize glare, the vehicle or the robot system could be equipped with this Plenoptic technology, which minimizes glare in a very significant manner. So here is an example showing how a regular camera would saturate a lot under sun's glare, and at the same aperture and exposure time settings, you can see that the image that we get after post-processing through the algorithm that we have developed, almost every piece of glare that was present in in a monochrome image has been removed. Like even the letters on the road, where it indicates that there is a hump in the road, are visible, which can help you in scenarios where you want to slow down and things like that. And also the sky, this is an extreme case, but you can see that there is a structure of clouds which is completely saturated in this image. So this is very useful from a glare reduction point of view, which was also evident in the Mobileye example that I showed you, which tells you where it can be used to minimize accidents that happen because of glare. And the other thing that I wanted to point out, which is very cool about our technology, is how can it be used to minimize accidents that are caused by road debris? So road debris causes 200,000 crashes every year, and that causes a lot of deaths as well. So the reason this is problematic is it is very small, and typical sensors are not able to see this very clearly. So what we are showing here is you can place a lot of commonly found road debris, like a wooden pallet, a cinder block, black tires, very small concrete blocks, a metallic rod, and a meshed fence. So these are all objects which are typically very hard to see. And as you can see, even if you use a 128 channel LiDAR with the best possible angular resolution, you can kind of pick out most of the objects if I tell you to look for them, but the metal rod is completely invisible. And with a regular camera, at nighttime, you could hardly see things which are on the road. Like in fact, one funny thing that I like to share is when I was doing this experiment, there was a person who was driving through the parking lot, and he almost drove into these objects, and I had to shout at him, or indicate to him that there are objects here. So it is proof that these objects are very hard to see, and with Plenoptic sensing technology, you can see that you can get contrast out of these objects, like even very strong contrast, even on a small brick on the road or a metal on the road. Black tire pops up, and this is the power of probing other aspects of the light field. And I think by using these signals, we can definitely make the roads safer than what they are today. So that's one thing that I wanted to highlight. And of course, other than these things, it can also be used to enhance visibility of the basic image. So if you had an RGB camera, if you add Plenoptic technology on top of it, it can be used to enhance visibility, which is very important for driving and mobility applications. So here is an example showing you that at night, it's very hard to see dark pedestrians. And what we did was, by using this technology, we are able to expand the dynamic range of the imaging system. So what I mean by that is, at the low end of the spectrum, where it's highly photon limited, we are able to extract signals which give you contrast when you plot a different property of the photon, not intensity, but you plot a different property. So with a regular camera, you can see that the pedestrian here is almost invisible, and then the vehicles here are almost not seen, whereas you get very good contrast on even curbs, persons, vehicles, and lane markers. So this is definitely very valuable information to have under low light conditions. Similarly, when you have fog and visibility is impaired, there's a lot of accidents that are caused because of fog. And since the way the photons get scattered can be modeled using a Mies scattering model or some other model that is relevant for the particle size of the materials, we are able to do dehazing of the scene. And here you can see that the drivable region is somewhat impaired in visibility, whereas when we plot a different property of the world using Plenoptics, you can see that the visibility significantly improves. Of course, this is not applicable for all types of particle sizes or obscurants, but if you model it correctly, you can identify how the photons are getting scattered, and you can remove those photons and improve the visibility of your scene. So this can be helpful to improve the visibility of your scene. So same thing can be done for rain as well. As I said, reflection removal is a very common thing for scenes which have high glare. So glare gets enhanced because of rain, and you can see that we are able to remove the photons which cause the glare and make the image almost glare free in a rainy environment. So these are some things which I wanted to share with you about how visibility could be improved. And I just want to show you one particular example of a very dark person in a tunnel with a very dark skin. So usually it's very hard to see people in shadows or in tunnels who are dark using LiDARs or camera systems. And here you can see that even with a 70 dB dynamic range, a base dynamic range of the sensor that has been used for this Plenoptic technology demonstration, it shows the contrast around the person compared to 105 dB HDR camera, which is currently shipping. So this is the power of using Plenoptics to enhance the image, and it has a lot of value in terms of the ability for the robot or the vehicle or any application to see the world better. And for indoor navigation, we have examples such as a glass detection, which are typically hard to do for humanoid or indoor AMR applications. So we are able to tell the presence of glass, the depth of the glass, and also the depth of objects behind the glass, because glass behaves in a very unique way, and dealing with the photons where it gets reflected or scattered from a material is only possible with Plenoptics technology, and we are able to do this for glass situations. And there are a few other things that I wanted to talk about in terms of our ability to do off-road navigation as well. So in off-road navigation, there is a lot of vibration between sensors. This can also be extended for applications where there's a lot of vibration, and usually when you have vibration, stereo camera systems fail because there is mismatch in extrinsics. And since we have more texture in the scene, we are able to do better online calibration than previously deployed approaches. So what we're trying to show here is if you move the camera even by a lot of error, by almost like 5-10 degrees, we are able to recreate the scene's depth with online calibration. So those are the things which help for off-road navigation. And here is another example showing negative space detection, like potholes and cracks and things like that, where which are present in an environment which is not very well maintained, like public roads. So if you go off-road, you would see a lot of negative spaces like potholes, ditches, and things like that, and you want to keep away from it. And we have some unique signals which you can use to train your algorithms to navigate around those pits. Yeah, to end with, I would like to share that this technology offers very robust perception in challenging scenarios, such as metal objects, lane marker detection, black tire detection, presence of curbs at night, and things like that. And as I mentioned, the power of this technology is to bridge the gap between very expensive, highly capable systems and very scalable, low-cost systems, but they don't have very good performance. So this kind of bridges that gap. And I think this is something worth trying out if your industry or your application needs a sensing modality which has the right balance of cost and quality. And thank you for your time and attention to listen to me for the last 30 minutes. Thanks a lot.
Thank you so much, Mahesh, for presenting on Plenoptic cameras for AI and advanced mobile robotics. Just to everyone joining us in the audience, if you haven't already, you can type your questions and comments into the conference chat box. And do not worry, if you've not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 4th annual Vision Spectra Conference. Thank you all so much for joining us.